Nuclear fission is the opposite of nuclear fusion. Rather than generating energy by ramming atoms together, it generates energy by splitting them apart. While it is less energy, it takes less input energy, and therefore it is already a technology that we use today. And while it is less energetic than nuclear fusion, it is still extremely energetic. The atoms nuclear fission uses are not the same as the atoms nuclear fusion uses. While fusion uses the lightest of elements, fission uses the heavier ones, typically uranium. The thing is, the atom with the lowest energy state of all is iron. That is why nuclear fusion in stars stops at iron, and why only the elements heavier than iron can be used for nuclear fission, although they tend to be the ones a lot heavier than iron because they pack more of a punch when split up. Here's how it works. Uranium is mined from the ground, but before it can be used to generate energy, it needs to be refined. The majority of uranium is the isotope uranium-238, meaning that it has 92 protons and 146 neutrons, 238 in total, which can't be used in nuclear reactions. However, a fraction of uranium is uranium-235, 92 protons and 143 neutrons. This is what is used for nuclear reactions. In a nuclear reactor, a neutron is fired really fast at an atom of uranium-235. This causes it to become uranium-236, which is more unstable, and the added energy from the neutron causes it to split up into lighter elements. But not only does it split up into lighter elements, it also releases energy and 3 more quickly moving neutrons. The energy can be collected, and the neutrons can go on to spark more reactions. This is a critical aspect to the function of a nuclear device. How many neutrons that stem from the reactions will go on to spark more? There are 3 neutrons that come out of each reaction, so if you want to make a nuclear bomb, then you want all of the neutrons to spark more reactions, because when that happens, more and more energy is produced until it explodes. But if you want to be more peaceful and just generate energy, then you need to install buffers that will absorb some of the neutrons so that the reaction doesn't spiral out of control. If these buffers fail, that is when you get a nuclear meltdown. In a nuclear reactor, the heat from the reaction is used to heat water. This water becomes steam and runs through a turbine which generates energy. Even if it isn't leveling cities, nuclear fission can be pretty bad for the environment. If a reactor has one of those aforementioned meltdowns, then it can completely irradiate a town for centuries. The Chernobyl meltdown in 1986 has left the town completely inhospitable to this day. The Fukushima meltdown sent radioactive water across the entire ocean for trace amounts to be discovered in California. Even a reactor working properly has negative effects on the environment. The hot water used to cool down some reactors is dumped back into the environment because it's not toxic. Despite that, the heat can change environments, which is not good for the wildlife. It also creates toxic waste that takes millennia to stop being dangerous. While this may seem bad, and a reason not to use this power source as much, it is still a lot better than fossil fuels, which spew carbon dioxide into the air and make our whole planet hotter. The results of fossil fuel use have destroyed a lot more environments than nuclear reactors, including ice sheets, coastal habitats, lands that are now in drought, and many more. Therefore, nuclear fission might be a good halfway point toward renewable energy. It isn't the best for the environment, but it's better than what we're already doing. All in all, nuclear fission is the opposite of nuclear fusion. We already use it for destructive and less destructive purposes. It isn't exactly clean energy, but might be a good short-term alternative to fossil fuels.